Okay, today's lecture we will go to solving differential equation using Laplace transformation. So this is something looks pretty familiar with you because you already learned this from the differential equation course. But here we will focus more in using the application by using step function, using impulse function, and etc. So we will use math with signals. So today is March 15, which is Friday. The readings are page 134 to 140. Solving differential equations using Laplace transformation. Next week, and Monday, we will go to solve the circuit analysis using Laplace transformation. So it will be on page 131 to 134. And there was supposed to be homework 10 and 11 on Monday, but they will be shifted to be in Wednesday, and the exam is shifted as well. So in March 20, which is Wednesday, we will also continue between page 131 and 134 about the circuit analysis using Laplace transformation, and also it will be the due date for homework number 10 and due dates for homework number 11. And keep in mind, homework number 11, do not stop it. So you already have the solution plus the mechanics. Or it will be ungraded. Just homework number 10 will be graded. Then on Friday, March 22nd, this is the exam day. Exam 2. I posted, I think, an announcement, and I think also there is on Canvas files about a sample exam, sample test with their answers. So you can look at the announcement. Try, after you finish the class, material class notes, after you finish everything, try to solve the sample exam by yourself with a 50 minutes timer. Then look at the answers, try to grade yourself, see how's your performance. So the sample exam, it can be as any legal test. Like it can be something similar to the test, actual test. So the same level. Then, the following week, which is in March 25th, Monday, we will start a new thing, which is Chapter 5, Fourier series. Fourier analysis. Okay? And of course, don't forget the tables, table 3.1, 3.2 are important. Then also we will discuss next week another 2 tables that are important as well. And this will be provided to you. Yes?
Oh, you said they'll be provided?
Yes, this table. So you don't need to worry about write this. You know you are allowed to have a note card 3x5. You can write whatever you need to on this. But don't try the tables, because all of them they will be provided. Table 3.1, 3.2, and also there is additional 2 tables that we will discuss next lecture about the circuit analysis. They all will be provided to you, so you didn't need to worry about it. So they will be part of the exam sheet. So when I look at this, you can see I think the last sheet, which is the tables. Any question? Okay, let's go to our today's topic, which is solving differential equation using Laplace transformation. I already mentioned at the end of last lecture about important properties about the derivative, such that when I have dx by dt, it will be s x of s minus x of 0 negative, while the second derivative, it is s squared x of s minus s x of 0 minus x bar 0. X bar 0, which is the derivative, the first derivative, the initial condition of the first derivative. Okay, let's see some examples. So example, let's solve this differential equation. dy by dt plus 2y of t equals u of t. And with initial condition, with y of 0 negative equals 0. Let's solve y. Okay, according to Laplace transformation, let's do the Laplace for the derivative. The derivative, it is s, y of s, minus y of 0 negative, then plus 2 y of s equals, what's the u of s in Laplace transformation? 1 over s, correct. Now, we know here the value the initial condition is 0. Therefore, this one will be 0. 0 initial condition. Then let's group y of s together. So it will be y of s, take a factor s plus 2 equals 1 over s. We need to calculate y of s. Y of s will be 1 over s plus 2. Okay? Or in other words, 1 over s squared plus 2s. But our target is to calculate y of t, not y of s. Now it's our turn to convert this to do Laplace inverse. To do Laplace inverse, we need to do partial fraction, right? Partial fraction expansion. Let's do partial fraction expansion. So it will be as c1 over s plus c2 over s plus 2. Okay? We know how to do this. We already discussed this a lot. Now, how can we do the partial to find the c's? c1 is actually y of s times s, or I would say s times y of s. S times y of s when s goes to 0, which is going to be as s times y of s, which will make 1 over s plus 2. When s goes to 0, this will make it 1 half. Then to find c2, it is s plus 2 times y of s, and substitute it when s goes to be negative 2. So it's going to be as 1 over s, because s plus 2 cancel each other. When s goes equal to negative 2, then it will be negative 1 half. As a result, we will say that y of s equals to 1 half over 1 over s plus negative 1 half over s plus 2. Let's take 1 half as a factor. So y of s will be 1 half 1 over s minus 1 over s plus 2. Now I'm ready to do Laplace inverse. Let's do Laplace inverse y of s. So this yields to be y of t. It will be 1 half. 1 over s is actually u of t. U of t. Then minus 1 over s plus 2. This is e power negative 2t u of t. Right? This is according to the table. You can go back to the table and see. Then that's it. This is the output, or this is the function. Then box your final answer. Now I solved this first order differential equation with easy way. I don't need to go use the homogeneous solution or the other part of differential equation techniques, while I can do it in estimate in an easier way. Any question? Let's do second order differential equation. Let's see how we can handle it. So this equation, which is e squared y of t by dt squared plus 6 y of t over dt plus 8 y of t equals 0 of t. Now, whenever we have differential equation, you know that we need to have initial conditions. Initial conditions must be given. If you have first order, you need to have 1 initial condition, second order 2 initial conditions, third order 3 initial conditions, and so on. So here, the initial condition is given as dy of 0 negative over dt, or in other words, y bar of 0 negative equal to 1, and we have y of 0 negative equal to 0. Now let's do Laplace inverse. So let's do Laplace inverse, first term, then second, third, fourth. So let's do the first one. D squared, or the second derivative. The second derivative Laplace transformation is s squared y of s minus s y of 0 negative minus y bar of 0 negative. Then let's do with the other term, the second term. The second term is first its derivative, so here it's 6. Then put a factor s y of s, then minus y of 0 negative. Okay? Then plus 8y of s equals, what's the other term? U of t. Not u of s, it will be what? 1 over s, right? Step function. Now substitute the initial condition. The initial condition, y of 0 equal to 0. Y of 0 equal to 0. Y bar of 0 will be 1. So let's do the simplification. This will make it s squared y of s minus 1 plus 6s y of s plus 8 y of s equals 1 over s. Now we have a thing which is the 1. Let's move it to the other side and take y of s as a factor. So we will take y of s as a factor. It will be s squared plus 6s plus 8 equals to 1 over s plus 1. Okay? Does this make sense? Now we need to calculate y of s. Y of s will be 1 over s plus 1 divided by s squared plus 6s plus 8. Since we have here s in the denominator, let's multiply by s over s. This yields y of s to be y of s will be 1 plus s divided by s squared plus 6s plus 8. Let's do it in a more simplified way. It will be s plus 1 divided by s cubic plus 6s squared plus 8s. How can I solve this? Let's do the partial fraction expansion. Before we do the partial fraction expansion, is this restriction proper? Yes. Then I'm ready. I don't need to do a long division. So let's find the roots of the denominator, or let's find what's called the poles. Try to find the root. S cubic plus 6s squared plus 8s equal to 0. Or in other words, you can say s and say s squared plus 6s plus 8 equals 0. This is a quadratic equation. You can say, you can find it anyway using the general formula or using any other formula. So it will be plus 2 plus 4 equals 0. So as a result, I can rewrite y of s in terms of the poles like s plus 1 over s plus 2, s plus 4. After that, I'm ready to do the partial fraction expansion. Okay, just like calculus, it's just math. Then it will be c1 over s plus c2 over s plus 2 plus c3 over s plus 4. Okay? Again, you know how to find the roots, right? The quadratic equations, the general formula, the others. Then, when we know how to do the partial fraction expansion, but here I'm trying to use this in a useful example, which is solving the differential equation. How to find c1, to find c2, c3. So c1 is actually s y of s when s goes to 0. This will make it s plus 1 over s plus 2 times s plus 4. Substitute when s goes to 0. This will make it 1 over 8. c2, s plus 2 times y of s. Substitute when s goes to negative 2. Then it will be as s plus 1 over s times s plus 4. Substitute this when s goes to negative 2. So the answer will be, I think here, negative 1 over negative 2 times 2, and will be 1 over 4. C3, it is s plus 4 times y of s when s goes to negative 3. Then it will be s plus 1 over s times s plus 2 when s goes to negative 4. Negative 4. Substitutes s equal to negative 4, so it will be as negative 3 divided by negative 4 times negative 2, so it will be negative 3 over 8. Now I know all of the c's. Let's substitute them in y over s. This yields y of s to be c1, which is 1 over 8 divided by s, plus c2, 1 over 4 divided by s plus 2, plus c3, negative 3 over 8 divided by s plus 4. Okay? I can rewrite it as y of s as equal to 1 over 8 times 1 over s plus 1 over 4 times 1 over s plus 2 minus 3 over 8 times 1 over s plus 4. Now, can you do Laplace inverse for this one? Yes. It's like basically exponential or step function. Then it will be, we do Laplace inverse y of s. This will be y of t. Then it's going to be as 1 over 8 u of t, because 1 over s is u of t, plus 1 over 4 e power negative 2t u of t minus 3 over 8 e power negative 4t u of t. And that's your final answer. And this is the answer of this second order ordinary differential equation. Okay, any question? Clear? So now, any differential equations, we are able to do this. If it's first order, second order, third order, I don't think we will not go higher than third order because it will be too complicated. I think this third order might be too hard, but we will focus on something that you can able to do it in short time. Now there is something that we know about the relationship between the transfer function and the differential equation. So any TF means transfer function. Any transfer function can be converted to ODE, which means ordinary differential equation. Any transfer function can be converted to ordinary differential equation. How and why? How can we do it? As we know, the transfer function h of s, it is the relationship between the output over the input, right? Y of s over x of s. And it's denominator over numerator. So we are able to convert this to be a differential equation. How? Let me give you an example. We assume we have y of s over x of s, or let me assume like this one. Assume the transfer function h of s equal to s plus 1 over s squared plus 2s plus 1. Now we need to convert this to a differential equation for mass. How? We know y of h of s is actually y of s over x of s equals s plus 1 over s squared plus 2s plus 1. Then let's do the multiplication for each part. Multiply by like this. Multiply this side with this side, this side with this side. So this yields to be s squared plus 2s plus 1 times y of s equals to s plus 1 times x of s. Okay, does this make sense? Then, what we will have, we can say that s squared times y of s plus 2s times y of s plus y of s equal to s x of s plus x of s. Now, how can I convert this to phasor domain or to time domain, from s domain to time domain? What do we need to do? Recall dx by dt equal s x of s minus x of 0. So what do you think x of 0 will be? I'm sorry, s x of s. S x of s will be dx by dt plus x of 0. Okay? That's how I can substitute any s x of s. Then also recall d squared x by dt squared equal to s squared x of s minus s x of 0 bar minus x bar of 0. Then, in order to find s squared times x of s, this will be d squared x of t by dt. Then, plus, since we have s x of 0, this will make it as d by dt. So 0 bar, let me see, so this will be x bar of 0 negative. Then since we have s, we're going to write it like this. So in order to simplify it, I'm going to assume 0 initial conditions. So we can avoid these initial conditions. When we have 0 initial conditions, This means x of 0 bar will be 0, x bar of 0 negative will be 0. So what this means, s, x of s, the equivalent is the derivative dx by dt. S squared x of s, the equivalent is d squared x over dt squared. And again, this is relative and only if 0 initial condition. Okay? So you can see that S is actually like ideal differentiator. So we'll make the derivative. S squared, the second derivative. S cubic, third derivative. Now let's go back to our example, which is here. I'm going to rewrite it here. So we start and we say s squared times y of s plus 2s y of s plus y of s equal to s x of s plus x of s. Now I'm going to assume 0 initial conditions. Then I can convert this to be, this is second derivative, first derivative, no derivative, first derivative. So this yields to be d squared y over dt plus 2 dy by dt plus y of t equals to d by dt x of t plus x of t. Then this is the second differential equation. So now I converted that transfer function into a differential equation. That differential equation is called, or actually this form is called linear constant coefficients differential equation. As a shortcut, we call it LCCDE, as linear constant coefficient differential equation. So this is called LCCDE form, which is basically convert this into differential equation. So it's going to be as you see here, constant terms multiplied by the differential equation. Constant 1, constant 1, constant 2. And the other thing, which is all of them as linear differential equation. Linear differential equation. LCCDE. Okay? Does this make sense? So you need to be aware of this form. I think we can see it in the homework problems as well. Let's do an example, or like problem in the textbook, problem 348. So given the impulse response as follows: h of t equals delta of t plus 6 e power negative t u of t minus 2 e power negative 2t u of t. So parts A, find h of s, which is the transfer function, or h of s. How to find the transfer function? We will convert impulse response from time domain to Laplace domain. So we can say h of s is actually the Laplace transformation of h of t. Then it will be delta, the Laplace transformation is 1, plus 6 e power negative t, 1 over s. 1 over s plus 1. So we can say 6 over s plus 1. Then minus 2 over s plus 2, because e power negative 2t, s plus 2. Okay? Then that question done. So you see, you can do it with 20 seconds. Part B, find poles and zeros of h of s. We need to find the poles and zeros in h of s. So let's look at h of s again. H of s is 1 plus 6 over s plus 1 minus 2 over s plus 2. what are the poles and zeros? Do you think the poles is -1 and -2 as we see here, or what do you think? Actually, with this form, we cannot tell. In order to find the poles and zeros, we need to have only a denominator, numerator, denominator. So we need to have this to be as n of s over p of s. This is not in that format. So what you're going to do, we basically look at the common factor. So the common factor here is s plus 2, s plus 1. So what I'm going to do, I'm going to say here is 1 times s plus 1, s plus 2 over s plus 1 times s plus 2 plus 6 over s plus 1 times this constant, s plus 1 times s plus 2 divided by s plus 1 times s plus 2, then minus 2 times s plus 1, s plus 2 divided by s plus 1, or 2 divided by s plus 2, and here s plus 1 times s plus 2. Okay? Again, why I choose s plus 1, s plus 2? Look at the denominator for the functions, the common, here and this one. Here the denominator is 1, and there is a negative 1. Okay? That's why I use s1, s plus 1, s plus 2. Now let's do more simplification. So s plus 1, s plus 1 here will cancel each other. S plus 2, s plus 2 will cancel each other. Okay. Do I need to remove s plus 2 here, s plus 2 here? No. So my point is to make all of them a common denominator. So it will be as all of it, after I cancel this and cancel this, all of them will have a common denominator. S plus 1, s plus 2, s plus 1, s plus 2, right? This is correct? Since everything has the common s plus 1, s plus 2, that's what I want, then the overall function remaining here, 1 times s plus 1, s plus 2, plus 6 times s plus 2, minus 2 times s plus 1. Does this make sense? Then I have it written in denominator over numerator over denominator, but I still need to simplify the numerator first. So it will be s plus 1 times s plus 2, it will be as s squared plus 3s plus 2 plus 6 times 2, 6s plus 6 times s, 6s, 6 times 2, 12, minus 2 times s, 2s, 2 times 1, negative 2, divided by, I take it as s plus 1, s plus 2, because I need to find the poles and the zeros, so I don't need to do the multiplication first there. Then we can group 3s, 6s, 2s, we can group 2, 12, negative 2. So after simplification, it will be here s squared, 3s plus 6s, 9 minus 2, 7, so plus 7s. Then here 2 plus 12, 14, minus 2, 12, so plus 12, divided by s plus 1, s plus 2. In order to make, we need to make it into a root format so we can find the poles and the zeros. So what are the roots of this one? You can use the general quadratic equation or try to see. So we will realize it will be s plus 3, s plus 4. Then what I'm going to do, I'm going to rewrite this, here is h of s, will be s plus 3, s plus 4, divided by s plus 1, s plus 2. Okay? Does this make sense? Now, the roots of numerator, there are zeros. The roots of denominator, they are poles. So we can say that zeros, when s goes negative 3 or s equal to negative 4. Poles, when s equal to negative 1 or s equal to negative 2. Then let's plot this into the x1 table. There is a new part, this is the imaginary part. So you will see that we have zeros, one like negative 1, negative 2, negative 3, negative 4. So the zeros written as O's, one at negative 4, one at negative 3, while the poles as X at negative 1, negative 2. Then that's it, probably. Okay? I can add just an extension for that problem, so I'm going to call it as B part 2, which is check stability. So this is easy, since I find the poles. Poles are at s equal -1, s equal -2. What does this mean? Is this stable, unstable? It's stable, exactly. So we can say it's stable. Why? Because they are all negative, and the real part is negative. The left half plane, left half plane. So it's stable. Okay? Let's do continue. Then part C, find LCCDE description. What does LCCDE mean? It means linear coefficient, linear constant coefficient differential equation. Basically, in other words, convert to differential equation. Convert to differential equation or linear differential equation. Okay? How can I convert this? Basically, look at h of s, which will be y of s over x of s, which is going to be s plus 3 times s plus 4 divided by s plus 1 times s plus 2. With this format, I don't think we can do it, so the best thing is to write it as polynomial for each one. And here I add to this question, assume 0 initial conditions. Okay? So any initial condition will be 0. 0 IC as initial condition. Initial conditions. Then I can say h of s equals, well, even I use I can say it's y of s over x of s. Well, the s, do the product, s squared plus 7s plus 12 divided by s squared plus 3s plus 2. Then do the products, s squared plus 7s plus 12 times x of s equals to s squared plus 7s plus 12 times y of s. Okay? S squared plus 3s plus 2. Okay? Now, let's do the products. This yields to be s squared x of s plus 7s x of s plus 12 x of s equals to s squared y of s plus 3s y of s plus 2 y of s. Again, we will assume again 0 initial conditions. This yields s squared as second order derivative, s as first order, and that's it. So it will be as d squared x of t by dt squared plus 7 dx of t by dt plus 12 x of t equals to d squared by dt squared y of t plus 3 d by dt of y of t plus 2y of t. Then to regulate it, I would prefer to put y on this side, so it will be d squared of y of t by dt squared plus 3 dy of t by dt plus 2y of t equals to d squared x of t by dt squared plus 7 dx of t by dt plus 12 x. Then this is the end. You can box it. Okay, is this clear? Any question? Let's go to part D. So part D, find the response y of t when x of t equals e power negative 3t u of t minus e power negative 4t u of t. Now, if you try to substitute this in the differential equation and try to solve this using the differential equation, this will be too difficult. Or even if you try to substitute this in the differential equation and convert the differential equation to Laplace transformation, this will make it also more difficult. Okay, what should I do? Use the transfer function. How? Let's convert this into x of s, to Laplace transform. X of s, this will be, since it's exponential, 1 over s plus 3. Then, minus, it's negative 4, so 1 over s plus 4. Okay? You agree with me on this? Just Laplace transformation. Now, we know the transfer function y of s equal to, h of s equal to y of s divided by x of s. So as a result, in order to find y of s will be h of s times x of s. Do we know h of s? Yes, we already found it. Do you know x of s? Yes, we just calculated here. Then let's substitute them. So h of s, I prefer to write this form s plus 3, s plus 4, or you can write the polynomial, but I prefer here so we can do some shortcuts. S plus 3 times s plus 4, or s plus 1 times s plus 2. Okay. Now, times x of s. X of s is 1 over s plus 3 minus 1 over s plus 4. Okay, we need to include this to make the product of this one and this one. So what should I do? Let's try to multiply, try to find a way by, make the product by s plus 3, s plus, actually we can make the product, multiply both sides. So it will be as s plus 2 times s plus 4 over s plus 1 times s plus 2 times 1 over s plus 3 minus s plus 3. S plus 4 divided by s plus 1 minus s plus 4, all of it by product s plus 4. So you will see that s plus 4 cancel each other, s plus 3 cancel each other. Then the denominator are the same for both, right? Then, so it will be the same denominator, s plus 1 times s plus 2. Then here we have s plus 4 minus s plus 3. So let's do simplification. So it will be here s plus s, 2s. Then 4 minus 3 will be 1, right?
Yeah, s minus s.
Oh, yeah. S minus s will be 0. 4 minus 3 will be 1. 1 over s plus 1. S plus 2. This is y of s. Okay? Now, we have y of s. The question is to find the y of t, not y of s. We need to do Laplace also. Laplace inverse. How do we need to do Laplace inverse? Let's do partial fraction expansion. Is this one strictly proper?
Yes.
Yes. So we can say this will be c1 over s plus 1 plus c2 over s plus 2. How to find C1? C1 equals to S plus 1 times y of s, substitute when s equal to negative 1, so the answer will be 1. Then C2 equal s plus 2 times y of s, substitute when s equal to negative 2, so the answer will be negative 1. As a result, we can say y of s equal to c1, which is 1, over s plus 1. c2 is negative 1, so here will be negative 1 over plus s2. Now I'm ready to do, this here will be partial expansion. I'm ready to do Laplace inverse. So to do Laplace inverse, we can say y of t equal Laplace inverse of y of s, then it's going to be as 1 over s plus 1, it's exponential equal negative t, u of t, then 1 over s plus 2, equal negative 2t, u of t, then that's the response. So here, again, I don't need to use the convolution, I don't need to use some other complicated things, just substitute them, and that's it. Okay, any question? Is this clear? Let's do another example in something similar to this. Okay, here, by the way, this are the tables, 3.2, 3.2. And this table we will discuss in the next lecture, which is related to additional table to the circuits. Anyway, let's do the problem 344. Okay, we already have the LCCB description, which is d squared y of t by dt squared plus 4 dy of t by dt plus 13 y of t equals to dx of t by dt plus 2x of t, and we will say assume 0 initial conditions. So part A, find the transfer function, or sometimes find h of s, whatever you call it. How to find it? Convert this to Laplace domain, and since there's 0 initial condition, you don't need to worry about s, x of s minus x of 0. You don't worry about s squared x of s minus x, s x of 0 minus x of 0, x bar of 0. So you don't need to worry about it. Just for any derivative, make s squared, second order, first order, make s. So it will be s squared y of s plus 4s y of s plus 13 y of s. You see, it's easy. S x of s plus 2x of s. Now put y of s as a factor, take x of s as a factor, so y of s as a factor, then it will be s squared plus 4s plus 13, then here x of s as a factor will be s plus 2. So let's make it y over x, so it will be y of s over x of s. This is the same as h of s, which is a transfer function. Then it's going to be s plus 2 over s squared plus 4s plus 13. Okay? Part B, find poles and zeros. Try to find the roots of the denominator and numerator. So we already know here h of s equal to s plus 2 divided by s squared plus 4s plus 13. So the roots of this one s equal to negative 2, while here the roots of this one, how to find the roots? So you can say it is, again, s squared plus 4s plus 13 equals 0. You can use the general formula. So in summary, it will be as negative 4 plus minus square root of 4 squared minus 4 times 1 times 13 divided by 2 times a, which is 2 times 1. Then s will be negative 2 plus minus square root of 16 minus it's going to be, I think it's negative 36 divided by 2. So it will be as negative 2 plus minus j3. It's going to be complex numbers. So as a result, we can say poles when s equal to negative 2 plus 3j, negative 2 minus 3j, zeros when s equal to negative 2. How to plug this into the x-plane mode? Here is x-plane mode, and here is 3j, here is negative 3j, this is negative 2. So you will see there's a 0 at negative 2, while the poles, there will be pole here, j3, pole at negative j3, such that this is the real part of s, this is the imaginary part of s. And that's the poles and the zeros. Also, is it stable or unstable? Look at negative 2 plus j3. We have a positive here. Does this make it stable or unstable?
Then we have some poles.
Exactly. It doesn't matter because we need to worry about the real part. Or all of the poles are in the left plane mode, then it is stable. So what we need to worry about is the real part, not the imaginary part. The imaginary part is positive, I don't care. Just make sure the real part. So it is stable. Okay? If the real part is 0, and we have one pole, then it will be marginally stable. Now, number C, find the impulse response. Find impulse response. Or in other words, find h of t. How to find it? We know the relationship between h of t and h of s. H of t equal Laplace inverse of h of s. Is this correct? Is this correct? The impulse response, h of t. Alright, so how to find h of t? H of t equal to Laplace inverse of s plus 2 divided by s squared plus 4s plus 13. Now, how we can solve it? We can solve it by doing the partial fraction expansion. So we Laplace inverse of c1 over s plus 2 minus 3j plus c2 over s plus 2 plus 3j. So c1 and c2, now to keep in mind, they will be complex quantities. So you can solve it. There is another way. We have 2. You can say it's s plus 2 over s squared plus 4s plus 13. Then equal to s plus 2 divided by s plus 2 all squared plus 3 squared. Then this yields to be, to make h of t equal e to the negative 2t, because there's a shift, 2t cosine, so there's 3 here, cosine omega is 3t u. Now, part D, find the response to input h of t equals e to the negative 2t u. When the input is like this, what should I do? How can I find the response, y of t? So basically, let's find x of s first. X of s will be 1 over s plus 2. Then in order to find y of s will be x of s times h of s. So x of s is given as s plus 2 divided by s squared plus 4s plus 13 times 1 over s plus 2. S plus 2 and s plus 2 will cancel each other. So y of s equal to 1 over s squared plus 4s plus 13. Then we need to find what's called the Laplace inverse. We can do like the other method by saying it will be 1 over s plus 2 squared plus t squared. Then we can do y of t, which is the Laplace inverse of y of s. Then it's going to be as, this is equivalent to the sine, so it will be 1/3 equal to negative 2t sine 3t u. And that's it. Because basically, in order to make it in this format, we will say times 3 here 1 over 3. That's how 1 over 3 comes from. Then that's it. That's what you need to know about the differential equation and application of differential equations in CMOS analysis. Then our next topic will be in S domain in how to solve the circuit analysis. Basically, that table, how to solve this using S domain. We know how to do this in phasor domain in circuit analysis, but now how about using S domain on phasor? So, see you on Monday, and again the exam has been shifted to the